next problem is called pad sum. If we're given the roots of a binary tree and an integer target sum, we have to return true if the tree has a root to leaf path such that adding all the values along the path equals target sum. A leaf is a node with no children. So in this case, 1 is a leaf node because it has no children. 13 is a leaf node because it has no children, and so on. And the root to leaf path is basically any path from roof to a leaf node. So in this case, let's say we have 5, 4, 11, and 7. This is one root to leaf path. There are many more here, and we actually have 4 of them. So we have 5, 4, 11, and then 2, and then we have 5, 8, 13, and then 5, 8, 4, 1. So there are in total 4 root to leaf paths. For each of those, we have to check if the total sum along that path, basically summing all the values. So in this case, if we have this 5, 4, 11, and 7, we will have this sum of 27 because 5 plus 4 is 9, plus 11 is 20, plus 7 is 27. And because the target sum in this case 22, for this, at least for this root to leaf, we will return false. But if you take a closer look, we have 5, 4, which is 9, plus 11 is 20, plus 2 is 22, which matches the target sum. So we have a root to leaf path that when we add up all the values in that path adds up to the target sum. So we return true. In the second case, we only have 2 root to leaf paths, so 1 and 2 and 1 and 3, and the total sums are 3 and 4, which neither of them are equal to 5. So we just return false. Basically, because we are doing the calculation inside the leaf nodes, we want to have the sum when we reach the leaf nodes by using a DFS approach. For each node, we will just be passing the total sum that we have calculated so far by including the previous and basically its ancestors, its parent, the parent of its parent, and so on. And basically, we will be checking in the recursion call if the sum is equal to the target sum. And if it is, we will propagate back the true, so the value true, because we know that there is a root to leaf path that adds up to the target sum. And once we reach the root again, we will know that there is a root to leaf path that adds up to the target. And when we look at the roots, basically we have 2 cases. There is no root to leaf path, or there is a root to leaf path that adds up to the target in the left or right subtree. So that calls for the recursion. So we will just call our helper function, and whatever the result of helper function after it has completed successfully, we will just return it as also the output of the main function has path sum. We will pass the root, we will pass the current sum, and the current sum will be just 0, and we will pass the target sum. And we will have, of course, our base case when the root is equal to null. We know that is no longer the leaf node. We are out of the leaf node because, and we have to go up the recursion tree. So we just have to return false. We don't have to check if the current sum is equal to the target sum. But if the current root doesn't have a left nor right child, that means it's a leaf node. So we just add the current sum and the value of that node to see if it matches the target sum. If it does, we will just return true. If not, we will just return false and propagate it up the recursion tree. Now for the recursion calls, basically for each node, it's the root to leaf path that adds up to the target sum can be either in the left subtree or the right subtree. But for each, we will just pass the new value of the current sum, and that value will be a current sum plus the node value that we currently have at the node that we are just visiting. And we will call it for the left subtree and for the right subtree. We have the OR operation because any of them will do. If we have a root to leaf path that adds up to the target sum in the left, we are good. If we have it in the right, we are good, and we will return true. Now for the time space complexity, basically as in the balanced binary tree, we will traverse through all the nodes in the, in the worst case, in all the nodes inside the binary tree. So that means that we have a linear time complexity proportional to the number of nodes in the binary tree, while for the space complexity, if we have a skewed left or right tree, that basically means we will have also a linear space complexity because we have to accommodate the stack required for the recursion calls in the left or right skew tree.